So last time we learned about the concept which is called Pfaffian, which is useful to count the number of perfect matchings. So how did we define the Pfaffian? Is we take the all perfect matching and then we added its weight. So we take all the perfect matching M, and for each perfect matching, you define the weight of M. And that weight is defined from the skew symmetric matrix A, which comes from the graph G with the orientation. So if the orientation is good, so Pfaffian, then all the weights of the M becomes same. So this actually counts the number of perfect matching. But for many graphs, there are no such good orientation. There are no Pfaffian orientation. So this Pfaffian may not be, actually counting the number of perfect matching accurately. Moreover, this may not even give you the information about whether the graph has a perfect matching or not. You take this adjacency matrix A and then give certain orientation and you compute the Pfaffian. And if it ends up become 0, then there could be two cases. Either, there are no perfect matching at all. So, this summation is summation over, 0 terms. That's why we get 0. Or there are actually perfect matching. Say there are two perfect matching M and M prime. But the weight of them, one of them is 1 and the other one is -1. So they cancel each other and we get 0. So we don't know which is the case. Whether there is no perfect matching at all or there is perfect matching but this cancellation happens. On the other hand, if we know that this Pfaffian is not 0, you compute the Pfaffian and it's not 0, then you can conclude that there exists at least one perfect matching. But the other case, if the Pfaffian is 0, we cannot really say anything. So one of the way we used last time to overcome this issue is that giving this orientation wisely so that all the term has the same sign. But another way we can try is that we consider this matrix A as a matrix with the variables. So that these weights here are not really number, but it's a multiplication of several variables, so that there is impossible to be cancelled each other. No terms cancelling each other. So for given G, what we want to do is we want to consider the skew symmetric matrix filled with variables. So we consider the skew symmetric matrix A, where each entries are variables. Say its ij's term is xij and ji term is negative xij for all ij edges of G with, say, I is smaller than j. Then this is indeed a skew symmetric matrix. And Pfaffian of A is now a polynomial in variables, say x sub e. E is in EG. Technically E is not ordered one, but I mean, you know what I mean. So okay, let's write it this way in more formal. ij is an h of g and I smaller than j. Then, I mean, not only the Fabian is a polynomial, but the determinant is also polynomial, and we know that the determinant is Fabian square. This is also a polynomial. And now we can say, because all these terms weight of m are indeed monomials, and then they don't cancel each other unless they consist of the exactly same edges. So now we can actually tell whether the graph has perfect matching or not based on this Fabian, or more generally the determinant. So we know that determinant of A is the zero polynomial if and only if G has no perfect matching. And proof is easy, as we already showed that determinant of A is Fabian square. And we know that this Fabian is zero polynomial if and only if G has no perfect matching. So this proves. It's because that all the monomial coming from different perfect matchings are totally different, so they cannot cancel each other. So number of terms in this Fabian, number of monomials in this Fabian is exactly the same as the number of perfect matching. So now, in order to check whether a graph G has a perfect matching or not, you need to just check whether determinant of A is 0 or not. Check. But there is some difficulty here because computing determinant of A is difficult. It takes a lot of time. But you might ask that, in the last lecture and before that, didn't we say that the computing determinant is easy? Yes, that is true. If we have a matrix filled up with numbers, then it's easy to actually compute the determinant because we know the row operation and we change this to row echelon form, and then we do the row operation to make it diagonal matrix. So these are 0, not diagonal matrix. Let's just say triangular matrix. And then you multiply the diagonal, then you know the determinant of this, and you know how the row operation from here to here have changed the determinant, so you can compute the determinant value. However, here, this determinant is not just number. This is a polynomial. In order to compute this polynomial exactly, then you have to actually go to the formula of determinant, and then there are at most m factorial terms. You have to compute them all. So computing this polynomial, finding this polynomial is difficult. So this equivalence seems not so useful at this moment. However, using that, we can develop some randomized algorithm to check whether the graph G has a perfect matching or not. Because, by using the observation that this determinant is easy to compute, when this matrix A is filled with numbers. So what's our plan is that when we have this A matrix, which is filled up with, filled up with variables. Let's say x1, 4. Here, what you do is you choose, some number, say y12 to y34, which lies in some field. And then these are numbers, and then you plug that in the corresponding variable. Then you get certain matrix filled with number. For that, you can compute the, say this is bold y, and you can compute the determinant of that matrix, which can be done in polynomial time. And then it happens to be non-zero, then you can conclude that the determinant A is non-zero polynomial. So there exists a perfect matching. But if this is 0, then again, you cannot really conclude. But if you repeat this with many, random tuples, and then it's always 0, then our intuition is that it's more likely that the polynomial is actually a 0 polynomial. If we want to prove this intuition, then we want to show that if determinant A is non-zero polynomial, then this event happens with not so high probability. That's what we want to show once this tuple is chosen at random. So for that, we need to show that if some polynomial is non-zero polynomial, then it doesn't have many roots. It doesn't have many zeros. So which is actually captured by this Schwarz-Zippel theorem. So what it says is that if you have a non-zero polynomial, it doesn't have too many zeros. Which is, which is what we already know when we have a determinant. We have a polynomial with one variable. But what it says is that even with a polynomial with several variables, we can also conclude a similar thing. So let's say we have a field F, and then S is a finite subset, and let P be a polynomial over the field. And let's say the degree of the polynomial is at most d. If we choose this y1 to ym at random from this S, then the probability that the polynomial evaluated at the random tuple is 0 is not so large, t over size of S. Oh yeah, I forgot to turn off the Wi-Fi again. Anyway, so I turn off anything that turns up in the iPad. Anyway, so this theorem says that if we have a non-zero polynomial, so meaning that if this determinant of A is non-zero, then the probability that we get this value 0 is not so big. So we want to use the induction on the number of variables m. If m is 1, then this is already something well known. We know that the one variable polynomial with degree d has at most d roots. And we want to use induction on m, so we assume the theorem holds for n-1 variables. And m is bigger than 1. So what we want to do is we want to use this base case, m equal 1 case. We use this to prove, the induction step. So what we want to do is we consider the last one as a variable, but rest of them as a number. Then you get a polynomial with one variable. There, you want to use the, this base case of the theorem. For that, let's say suppose that xm occurs in at least one term with a non-zero coefficient. Otherwise, it is a really polynomial with a n-1 variable, so last coordinate is irrelevant, so that the induction hypothesis gives us what we want. So now we consider this as a one variable polynomial with the variable xm. Then we can actually write it with this. So we categorize all the terms in terms of the degree in the last variable. And let k be the largest number such that pk x1 to xk minus 1 is a non-zero polynomial. And let curly epsilon be the event that we have this pk term does not vanish after putting the number y1 to yn-1. No, the other way around. It's that it vanishes. Then, by the induction hypothesis, what do we know? This is a polynomial with n-1 variable. And then the event that it becomes 0 once you put in randomly chosen numbers here. The probability that this curly epsilon holds is at most t minus k over s, as pk has degree at most t minus k. Because this term has a degree I, so this term must have degree at most t minus I. Because every term here has degree at most d. And if this pk y1 to yn-1 is not empty, and the values y1 to ym-1 are chosen. So we conditioning on the event that the curly E doesn't happen. Then what do we have? Then this P now really becomes a polynomial in one variable because every other variables are chosen except the last one. Then we have a one variable polynomial, say Q xm, which is P y1 to ym-1, comma xm. And what's the degree? Degree is k. Because we assume that all the terms here with the degree bigger than k are, vanishing. So, and also the term with the degree k survives here. So because we assume that this pk is non-zero after evaluating at y1 to ym-1. So there are at most k choices of xm with qxm equals 0. So once we chose m-1 first coordinate, and then the number of choices for the last coordinate is at most k. Hence, the probability that p of y1 to ym equals 0, assuming curly E doesn't happen, conditioning on that, is at most k over size of S. Then what we know, the probability that this P evaluated at y1 to ym is 0 is at most that probability that this happens, assuming this curly E times probability of curly E happens. This is the conditional probability. Plus again, this is 0, assuming curly doesn't happen, times curly doesn't happen, the probability that curly doesn't happen. And here, we know that this term is at most 1, so we can just write the upper bound as a probability of curly E. And on here, on the second term, we know that this term is at most 1, so we can just write the probability of, this conditional probability. And then we already know that this and this shows that that's at least at most d minus k over s plus k over s, which is at most d over s. And this is exactly what we wanted. So this shows that the theorem holds. So using that, we can find the randomized algorithm which succeeds with a high probability and check whether the graph has a perfect matching. So all the deterministic algorithm, algorithm will give you an answer and you want to make sure that that answer is correct. And you want to also make sure that that algorithm takes not too long time. But some cases, such an algorithm may not exist. Then instead what you want to aim at is you come up with some randomized algorithm. And then for that you want to make sure that it doesn't take much time, and then it has good accuracy. Meaning that in this case, we have two cases. If G has perfect matching, and if G has no perfect matching, and there are two cases. It has a perfect matching, and then your algorithm say yes, then it is good. No, but then it is not good. And yes, and no. So these are the right answer. what we aim for is that in each case, we want to make sure that this happens with high probability. This correct answer happens high probability, and this has low probability. That's what we are aiming for. So, in this case, this determinant is non-zero polynomial, and this determinant is a zero polynomial. So what we do is we choose some field, let's say real number, and then choose S inside of the field with size 2D. So you just choose arbitrary 2D real numbers and then take it as S. And we choose a random element, y1 to ym. So m is here depending on the number of edges, because we are considering the determinant. And this A is the skew symmetric matrix filled up with variables. So we choose this random tuple y1 to ym uniformly as random. The one of 2D to the m elements, each element are picked with probability, same probability, 2t to the negative m probability. And you check that whether determinant of A is 0. So if determinant of A is non-zero, then return yes. If determinant of A is 0, then repeat. And we don't want to repeat too many times, so just repeat k times. And out of this k times, if you get at least one instance of having the determinant not 0, let's write it this way. AY. As this is a matrix filled up with numbers, so you can actually check this in polynomial time. So this is our randomized algorithm. If G has no perfect matching, then the determinant is polynomial. So you always get.
우선 맥을 잠금해주셔야 합니다.
Sorry. I should have turned it off. Anyway, so if determinant was 0, if G has no perfect matching, then you always get this case. And after k times of determinant being 0, return no. So you will always get this. So this is 100% and 0%. So we want that in this case, we want to get right answer with high probability. So this is as high as we get. And the other case, we will never get the wrong answer. What about the case when G has a perfect matching? This determinant is a non-zero polynomial. So the probability that we get wrong answer in one time checking is at most d over s, which is at most 1 over 2, at most half. And then we repeat this k times, and each event are independent. So the probability that we get the wrong answer is at most 1 over 2 to the k. And then probability that we get the right answer is at least 1 over 2 to the k. So depending on how accurate we want the algorithm to be, we can choose k to make sure that this is accurate enough for our purpose. Then we can make this high and we can make this low. So this serves our purpose of giving the right answer with high probability. while the number of times that we have to perform, the length of time of the algorithm is that you have to, as long as we can choose these random numbers in an efficient way, choosing random number means, if we can do that in a efficient way, then checking this determinant of the matrix with numbers takes the polynomial time, and then you just repeat k times. So assume, so the learning time is polynomial in k and n, where A is the n by n matrix. So this provides a randomized algorithm that can check whether a given graph has a perfect matching or not. So this finishes the chapter 2. Now we want to move to the chapter 3.